So I'm going to show you how to write a noble gas configuration by looking at the table. You don't even need to use the relative energy of orbital that we showed you. So this is a second method to write electron configuration that's called noble gas configuration. How we are going to do that? First of all, number of outer shell electrons are predicted by these group numbers, which are followed by letter A. All right. And if I look at periodic table, can I write a noble gas configuration? Let's check. Let's look at group 1A. If I ask you number of the electrons in the outer shell or valence shell is what? And you might ask, why do we care about outer shell electrons, which we call them valence shell? Well, we care because those are the most reactive electrons, because they have maximum number of energy. Why? They are furthest away from the pool of protons. So chemistry is about understanding reaction between substances. We want to understand reactions between elements. We have to understand energy of electrons. We have to understand the real players in chemistry, which are electrons. Obviously, electrons in the outermost shell are the most important one. So you want to know number of electrons of outer shell? Look at this column number, which is followed by letter A. 1 electron. How about electrons in the next one? Group 2A, 2 electrons, and those electrons are in s orbital. And if I go to the next column, and this is the main group element, is 3A, it must have a total of 3 electrons in the outmost shell. I can't place more than 2 electrons in s orbital, so the third electron go to p orbital. If I go to the next column, 4A, it has got 4 electrons in the outer shell. 2 of them would go in s, and then there are 2 left which have to go to p orbitals. So what do you expect? General formula: N S2 and P2. You might be asking, what is N? What is N here? N is obtained from the period number. Do you see? This is period 1, period 2, period 3, period 4. This is period 5. See? 1, 2, 3, 4, 5. This is period 6, period 7. And remember, this belongs to here. So this is period 6, and this is period 7, because these elements came from inside the periodic table. They belong this space, remember? So N is defined based on the orbital that we are talking about. If you are dealing with s orbital and p orbital, there is a formula for N. So for s and p orbitals, N is equal to period number. What do I mean by period number? Let me ask you a question. Suppose I want to look at number of electrons in phosphorus, let's say. So, or arsenic, or anything else. So can I say, because this is in group 5A, there are 5 electrons in the outer shell. 2 of them in S, 3 of them must go in p orbital. But which s orbital and p orbital are we talking about? Because phosphorus belongs to period 3. So for phosphorus, there are 5 electrons. There is n is equal to 3, 2 electrons in 3s, and then we have got 3p left with this. And I don't know if a slide is big enough for you to see. That's what prediction is. 3s2, 3p3. So do you see? You can predict number of valence electrons, outer shell electrons, by looking at the location of element inside periodic table. That is why periodic table is so important to chemists. All right. So I'm going to go to next. Let's say this group is 6A. You must have 6 electrons. Out of these 6 electrons, all of these member of column 6A, they all have 6 electrons in the outer shell. 2 plus 4 is 6. Only 2 of them can fill up s orbitals, so 4 would be left for p orbitals. Again, value of n depends on the location of element. I can choose the element. Let's say element 116. It's in group 6A, it must have 6 electrons. The electrons are 2 of them in S and 4 of them in P. I want to determine the value of N, which shell S and P belong to. So I'm going to go here, 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 here. That is period 7, so 7s2, 7p4. Yes? Although this table doesn't show element 116, but there is a lab in Lawrence Berkeley lab in Berkeley is making new elements by changing number of protons of an element. At the time this table was made, these elements were not known. Today, we have discovered element 119. Why do we make new elements? Because we want to study the property of new elements. And then if they are useful for us, we can mass produce them, bring them into the market. So for example, one of those elements made is americium. It didn't exist on Earth. It is a man-made element by changing number of protons of the atoms. It's named after America. It's americium. And this element was found an application which you and I are using every day. Americium is used as part of the smoke detector. So every one of us, when we sleep at night, we trust americium as part of the detector, of a smoke detector, which we can buy for $5. Is this reason that we make new elements? We study them, we see if we can use them, then we mass produce them. For example, there is element of californium named after California. Okay, if I continue, go to, these are the groups that will follow the same rule. Now I want to go get out of the main group elements and go to transition metal. Let me clean up my whiteboard and show you, if I'm dealing with transition metal, what is the rule? How can I determine number of valence electron? How could I say which orbitals these outer shell electrons belong to? So I'm going to go to next here. This is the first column of transition metal, and it has got 1 electron in the orbital. And if I go to the fifth column, see 1, 2, 3, 4, 5. There is 5 electrons in d orbital. And if I go to column 10 of transition metal, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have got 10 electrons in d orbital. How do I know which d orbital are we talking about? This is on 4th shell, 5th shell, 6th shell. I'll give you a formula pretty soon. And if I go to the inner transition metal, they have got their electrons, their outer shell electrons in 4f. And this next inner transition metal row, which are called octanide, they have their outer shell electrons in 5f. So I'm going to formulate this, give you a simpler method of predicting valence electrons using periodic table.